These are the answers to homework 1G. Here are the definitions I'd like you to know. Now let's go to the questions. Number 1, rank the following acids from weakest to strongest. The acids given are the triprotic acid H3BO3, and then two intermediate forms, H2BO3- and HBO3 2-. H3BO3 is a weak acid. It has an equal numbers of O's and H's in its formula. When you get to the intermediate forms, the ion forms, you cannot use the ratios of oxygens to hydrogens. So whenever you have intermediate forms of a polyprotic acid, successive hydrogens are always harder to pull off, which means the acids get weaker and weaker. So therefore, the most ionized form, the HBO3 2-, will be the weakest acid, and then the H3BO3, which has all of its hydrogens attached, its initial form, that's going to be the strongest. The H2BO3- will be the one in the middle. Number 2, a solution is 0.050 molar in sulfurous acid. Calculate the concentrations of all the species in the sulfurous acid solution and then calculate the pH. So sulfurous acid is a diprotic acid. We answer the question by doing each ionization successively in a row. First ionization, the H2SO3, reacts with a water molecule to form a hydronium and the bisulfite ion. The equilibrium constant for this reaction is called the Ka1 for sulfurous acid, and it can be looked up on handout 3. To determine what the equilibrium molarities are, we're going to write an ice table. It said the concentration of the sulfurous acid was 0.050. Before it ionizes, there would be no products, and some small amount of this will ionize because it's a weak acid, so we'll call that X, and you'll form X molarity of hydroniums and X molarity of bisulfite ions. Equilibrium molarities will be 0.050 minus X, X and X. The equilibrium constant expression for this particular reaction will equal an equilibrium constant called the Ka1 for sulfurous acid. That'll be hydroniums multiplied by bisulfite divided by sulfurous acid. By looking up the Ka1 value, which is 1.5 times 10 to the minus second, and plugging in the equilibrium molarities, we can solve this for X, either doing it by the quadratic equation to get the answer exact, or by ignoring the X in the denominator and solving the more simple algebraic expression, which leads to 2.7 times 10 to the minus second. Now, when you test the 5% rule for this one, this comes out way above 5%. It actually comes out 55%. So therefore, the assumption that X is close to 0 is not a good assumption in this case, and we have to do recycling. So you're now going to repeat the calculation, but instead of assuming the negative X in the denominator is 0, you're going to replace that with the 2.74 times 10 to the minus second. You will calculate the answer for X with this, which comes out to be 1.8 times 10 to the minus second. And then we're going to take the 1.84 times 10 to the minus second, put that in the denominator, so go 0.050 minus 0.0184, and we're going to continue this process as many times as it takes until you get the same answer twice in a row to two significant figures. And if you continue that, you're going to wind up getting an answer of 2.1 times 10 to the minus second twice in a row, so we can assume this will be the correct value for X. So after the first ionization, we've now determined X. What are going to be the molarities of the species present? Look at the equilibrium line in the ice table. These will be the three equilibrium molarities. The sulfurous acid will be 0.050 minus 0.021, so its molarity is 0.029. The hydroniums and the bisulfites both equaled X. They're going to be 0.021. That's the first ionization. Now the second ionization occurs. The bisulfite ion will react with water to produce a hydronium ion and the sulfite ion. So this is going to be the second equilibrium or the second ionization of the acid, and the equilibrium constant for this reaction is called the Ka2. The initial molarity is not the 0.050 we started in the first part of the problem. That was the molarity of the sulfurous acid. The bisulfite concentration is located at the top of this slide. It's 0.021. The hydronium concentration is not 0. It's also in the solution at this point. It's 0.021. But there are no sulfite ions present. That's going to be 0. The reaction will have to proceed spontaneously to the right because there are no sulfite ions in the solution. The reverse reaction cannot occur. And I'm going to use a different variable. I'm going to say minus y for the bisulfite, plus Y for the hydroniums, and plus Y for the sulfite. The equilibrium molarities here will be 0.021 minus Y, 0.021 plus Y, and Y. The equilibrium constant expression will equal the Ka2 for sulfuric acid, hydroniums times sulfite over bisulfite, and we can plug in the equilibrium values as well as the Ka2, which comes from handout 3. In this problem, the plus Y's and the minus Y's can be assumed to be really small. We'll ignore those, and that will allow the 0.021 on the top and the bottom to cancel out. So this just simplifies to Y equals 1.0 times 10 to the minus 7th. So now we can amend our answers from above. The H2SO3 concentration wasn't affected by the second ionization, so it stays 0.029 molar. The hydronium concentration is going to be what it was initially, but on the equilibrium line under hydronium, it says plus Y. So you have to add 0.000002, or 1 rather, and that actually doesn't affect the 0.021, so it stays 0.021 molar. The bisulfite concentration is 0.021 minus 0.000001, and once again, that's so small it doesn't affect the number, it stays 0.021. And then the sulfite concentration is our Y value. That was 1.0 times 10 to the minus 7th. Part B says, what's the pH of the solution? That comes from the hydronium ion molarity. So if you take the negative log of our hydronium ion molarity, you'll get a pH to two significant figures of 1.68. Problem number 3. A solution is 0.30 molar in sulfuric acid. Calculate the concentrations of all the species present and calculate the pH of the solution. Similar problem. In this case, the acid we're given is a strong acid, H2SO4. Now, we had said that if you have a strong acid, you assume it completely ionizes, and I wasn't 100% truthful about that with you. Even going back to Chem 1A, I was saying the same thing, and I wanted to save it for now as a surprise. Ms. Lagai almost gave it away last semester because she had a Chem 3 instructor that actually told her how this worked, but I wanted to keep it a secret until Chem 1B. When you have a polyprotic acid that's a strong acid like H2SO4, what it really means is that first hydrogen comes off 100% of the time. That's why you will not find a Ka1 value for sulfuric acid in handout 3. It happens 100%, essentially the Ka1 value would be infinity. So for the first ionization here, you assume complete ionization. So the sulfuric acid was 0.30 molar, and before it ionizes, there's no hydroniums, no bisulfate ions. And because it's a strong acid, all 0.30 of it react away. In a 1-to-1 ratio, it'll form 0.30 molar of hydroniums and 0.30 molar of bisulfate. So therefore, the final molarities, they won't be equilibrium molarities because it doesn't establish an equilibrium. You'll actually have no sulfuric acid molecules in the solution at all, but you'll have 0.30 molar hydroniums and 0.30 molar bisulfates. So after the first ionization, the molarity of the sulfuric acid is 0, the molarity of the hydroniums are 0.30, the molarity of the bisulfates are 0.30. Now the bisulfate ion is the intermediate form of sulfuric acid. This one is not a strong acid. That second hydrogen does not come off 100% of the time. It will actually have a Ka2 value listed in handout 3. So we're going to write the reaction for the intermediate form of the sulfuric acid, the HSO4-, which has been created after the first ionization with water to form a hydronium and a sulfate. And the initial molarities are the ones we just calculated after our first reaction. It's 0.30 molar in bisulfate, 0.30 molar in hydroniums, and there was no sulfates present. So because this is not a strong acid, an unknown amount of it will react away. I'll call it Y. Will form Y hydroniums and Y sulfates. The equilibrium molarities are 0.30 minus Y, 0.30 plus Y, and Y because we love you. The equilibrium constant expression for this will equal the Ka2 for sulfuric acid. So that would be the concentration of hydroniums times the concentration of sulfates over the concentration of bisulfate. And if you look up the Ka2 value for sulfuric acid, it's given as 1.2 times 10 to the minus 2nd. In this problem, the plus Y and the minus Y, we cancel out. The 0.3s cancel out, and Y equals 1.2 times 10 to the minus 2nd. So now we've calculated that there are no sulfuric acid molecules in the solution. The hydronium concentrations are going to be 0.30 plus the 1.2 times 10 to the minus second Y value. So the molarity of the hydroniums is actually 0.31. The bisulfate concentration is 0.30 minus the Y value. That turns out to be 0.29. And the sulfate concentration turned out to be 0.012. Part B, the pH of the solution, that comes from the hydronium ion concentration. We take the negative log of 0.31 molar, and to two significant figures, we get a very low pH of 0.51. Question number 4. A solution is 0.18 molar in ammonium chloride. A, which ion is reacting with water? So ammonium chloride is made up of an ammonium ion and a chloride ion. Ammonium is a conjugate acid of ammonia, which is a weak base, so the ammonium ion is a weak acid. Chloride comes from HCl, which is a strong acid, so the chloride is a non-base. So because the ammonium ion is the weak acid, a chloride ion is a non-base, it's the ammonium ion that's going to react. B, is the solution acidic or basic? Well, ammonium's acting as an acid, it's going to be an acidic solution. C, what constant is used to calculate the pH? You will need the Ka constant for the acid, for the ammonium. You can look that up in handout 3. The Ka for ammonium is given as 5.6 times 10 to the minus 10th. D, calculate the pH of the solution. You'll do this by writing the hydrolysis reaction, which just means the reaction of the ammonium ion with water. And the ammonium ion is an acid, so you have to be able to write a reaction for what a Bronsted-Lowry acid does. Acids give up hydrogen ions. So the ammonium ion will give up a hydrogen ion to water, forming an ammonium ion, and you'll form ammonia. We'll do an ice table for this. The concentration of the salt was 0.18 molar, and because there's one ammonium in the formula, I'll go 1 multiplied by 0.18. There's the concentration of the ammonium, and there'll be no products. Some unknown amount of this will react. You'll form X hydroniums and X ammonias. And at equilibrium, you'll have 0.18 minus X, X and X. The Ka expression for the reaction is products over reactants. And we use the Ka value of 5.6 times 10 to the minus 10th. That's going to equal X squared over 0.18 minus X. We ignore the X in the denominator. And then when we solve for X, it comes out 1.0 times 10 to the minus 5th, which is less than the 5% rule. So this is the correct value for X. X stood for the hydronium ion molarity. So if we take the negative log of the hydronium ion molarity, we'll get the pH of this salt solution, which turns out to be acidic, 5.00. Number 5, a solution is 0.025 molar in sodium nitrite, which ion is going to be reacting with water. The sodium ion comes from the base sodium hydroxide, so the sodium ion is a non-acid. Nitrite comes from the acid nitrous acid, which is a weak acid. So the nitrite ion is a weak base. So therefore, the weak base is going to be the one that reacts. It'll be reacting as a base, and so therefore, it's going to make the solution basic. What constant do you have to use? You have to use the Kb for the nitrite ion, but it is not in handout 3. So if you don't know the Kb for a particular base, you look up the Ka of its conjugate acid. And the Ka for nitrous acid was given in handout 3. It was 4.0 times 10 to the minus 4th. So we can calculate the Kb for nitrite by going Kw divided by Ka, and that turns out to be 2.5 times 10 to the minus 11th. Now, part D, calculate the pH of the solution. We have to write the hydrolysis reaction for the nitrite ion acting as a base. So Bronsted-Lowry definition, what does it do when it reacts with water as a base? It accepts a hydrogen from the water, turns into HNO2 and a hydroxide ion. Writing an ice table for this, we need to know the initial molarity for nitrite, which technically is not given. They say 0.025 molar sodium nitrite, but sodium nitrite has 1 nitrite in the formula, so you go 1 multiplied by 0.025, and that's the molarity of the nitrite ions. We'll assume there's no products before the reaction occurs, so some small amount of the nitrites will act as a base and react away, and they'll form X amount of nitrous acid molecules and X amount of hydroxides. Equilibrium molarities are 0.025 minus X, X and X. The equilibrium constant expression for this will equal the Kb for the nitrite ion. That'll be nitrous acid times hydroxide over nitrite. We have calculated the Kb value from above, 2.5 times 10 to the minus 11th. And if we ignore the x in the denominator, we can say that is equal to x squared over 0.025 and solve for x. And x comes out 7.9 times 10 to the minus 7th, which is smaller than 5%, so we can accept this as our x value. Now, x stands for the hydroxide molarity, so the negative log of that will be the POH. So the negative log of 7.91 times 10 to the minus 7th gives us a POH of 6.10. So the pH would have to be 14 minus that, and 14 minus 6.10 gives us a pH on the basic side of 7.90. Problem number 6. A 0.100 molar solution of sodium iodide, NaIO2, has a pH of 10.85. A, write the equation for the hydrolysis of NaIO2. You do not write an equation NaIO2 plus water. You have to figure out which ion reacts with water. So in this particular example, the compound contains a sodium ion, which is the conjugate acid of sodium hydroxide. Sodium hydroxide is a strong base, so the sodium ion is a non-acid. It doesn't react. IO2 minus comes from the acid HIO2, which only has one more O than H in the formula, so iodous acid's a weak acid, and so the iodide ion must be a weak base. That's the one that's going to react. So the reaction you write is the weak base iodide ion reacting with water, gaining a hydrogen to form HIO2 plus OH minus. B, write the equilibrium constant expression for the hydrolysis reaction and tell if it's a Ka or Kb. Well, iodide's acting as a base, so the equilibrium constant expression is going to be a Kb expression, and it's going to be products over reactants, the iodous acid molarity times the hydroxide molarity over the iodide ion molarity. C, calculate the value for the equilibrium constant Kb. So we're going to do that with an ice table. So if we take our reaction and we take the molarity of the iodide ions, they said it was 0.100 molar in sodium iodide. There's only one iodide in the formula, so 1 multiplied by 0.100 is the molarity of the iodides. There's no products before the reaction occurs. Some amount of the iodides will react as a base, forming X molarity of iodous acid and X molarity of hydroxide. So the equilibrium molarities will be 0.100 minus X, X and X. If we now write our Kb expression and we plug in the equilibrium data, we wind up having two variables, and we have to get X first before we get the Kb, so there had to be a clue in the problem, and the clue was the pH was 10.85. That's a measure of hydronium concentration. Our solution has hydroxides in it, so I'm going to convert that into the POH by going 14 minus 10.85, and the PaOH of this solution is 3.15. If I know the POH, I can take the anti-log of the negative POH, and that's going to give me my hydroxide molarity, and that's important because that's X. So that's going to equal the anti-log of negative 3.15, which turns out to be 7.1 times 10 to the minus 4th. So that's the secret way to get X. If we plug the 7.08 times 10 to the minus 4th in place of the X's, don't ignore the X in the denominator. You'd be adding error to your calculation, but actually multiply it all out. We get a Kb value of 5.0 times 10 to the minus 6th molar. D, calculate the acid ionization constant for HiO2. Wasn't listed in handout 3. You have to calculate it from the data here. And if you know the Kb of its conjugate base, IO2 minus, you can calculate the Ka of the acid HiO2. It comes from Ka times Kb equals Kw. So if we go the Kw divided by the Kb value for the iodide ion, we're going to calculate the Ka for iodous acid, which comes out to be 2.0 times 10 to the minus 9th.